in the second half of the 20th century that dark matter problem arose. I don't know. I don't remember. I don't remember who was the first to measure galaxy curve rotation. It might be. It might have been earlier, but I don't know.
I'm just trying to make sense of whatever argument you're making. If you're saying like this is old stuff, it was in a different framework or whatever the case is, and it sounded like dark energy and dark matter was older than the virtual photons.
It doesn't matter when in time to define what is the concept. It's not that I can use an old concept today, and I might have used a new concept 1 century ago. What it doesn't matter when it happened in history.
Well, I'm asking you to clarify your argument. I'm trying to figure out what is the distinct difference between the two concepts. I don't know if I've heard it yet.
I tried to explain it to you. The photons are not a new concept. It's a way of making a calculation, of technically making a calculation. It's not introduced a new particle, such as the charm quark, such as the top quark. It's not I have introduced a new physical object, which I don't know what it is, such as dark.
Isn't that what they had to do with dark energy and dark matter? Did they not have to do that same thing?
No, it's not the same, because it's something. It's not like we have. It's not like we take the Newton or Einstein, if you prefer, gravitational law, and we want to make the calculations. Oh, look, the calculation we make was just approximation because it was approximating the galaxy as a point. No, it's not a point. It's a disk with distribution. We make the calculation. It's not doable. We have to make a new calculation in a very different way. Let's do it perturbatively, and then introduce, in order to do this, the missing mass. No, it's not that. It's not that. It's I'm using what I know about gravity, about gravitation, about Einstein or Newton, and then use this to predict what the velocity profile as a function of radius, of distance to the galactic center is, if I presume that the mass distribution is proportional to the light distribution. With this assumption, which was the one that was the common one up to a point, it was not compatible with this hypothesis. So the hypothesis has to fall. It has to go away. The hypothesis is that the mass is distributed the same way as the light. Or alternatively, since you like alternative explanations, gravitational law is flawed. It's different. So you have to come up with a different gravitational law, and this hasn't worked. There's not been any proposal which was describing the data accurately, and so they had to resort to missing mass or dark matter, whatever. And then you have studied and you have predictions with this, because yes, you have. I've just translated a book by Andrew Ponson about simulations used in astrophysics, in weather forecast and in astrophysics, and it turns out that the dark matter the guy, you should probably read the book. It's called The Universe in a Box by Andrew Ponson. He's a British.
Called the what? You was breaking up. Called the what?
Andrew Ponson, The Universe in a Box. He describes, and he says that when he was a student in early 2000, he thought that the explanation of dark matter and dark energy were just an ad hoc explanation, and didn't believe them. He says that because it sounded like a made-up explanation, which was too convenient. Okay, we don't understand this. Okay, we make up something, and we introduce some dark matter and energy, and we're fine. And then by studying very deeply and understanding it and seeing what the prediction power of this is, he totally changed his mind. But I didn't change mine because I only translated a popular book, so I don't know all the technical details. He does, and so maybe you can write to him. He's also on Twitter, by the way, and ask him about dark matter. I'm not an expert, so I can only tell you what I've learned from the physics course when I was a third-year student, and from reading about popular books. By the way, dark energy was not even mentioned when I was a student. It was something that came up in the late 90s, early 200s, because of the discovery of the accelerated expansion of the universe. So I really don't know.
You mean the assumption? Because I still don't even know why they went to that. No one said this is the reason, this is why this is the more viable framework to have an accelerative expansion of a universe.
That was
no one explained.
That was measured. It was measured, the expansion, using some astrophysical techniques. So the universe was thought to be. I said it before in the space. When I was a student, when I was a PhD student, I followed a cosmology course. By the way, by the same that I was quoting yesterday, who was teaching at the time, who was teaching a cosmology course. He's a particle physicist, theoretical physicist, but he was teaching a cosmology course. And the problem at that point was that the universe was flat, was too flat for, in order, you had to be, there had to be a fine tuning of the parameters in order for it to be not accelerating and not contracting exactly.
And a fine tuning requires a fine tuner. But go ahead. Now we're finding some common ground. Why you about to come with some type of solution to the flat universe? What'd they do? How did they solve the flat universe problem, the flatness problem? Oh shit.
Yeah, I can't hear him if he's speaking.
You know what's crazy? He'll never go to the TL and say, yo, Sacred gave me all this time to speak uninterrupted. Like I was getting crazy and he just kept it calm and let me dominate the conversation so I get my shit off from earlier. After he ain't never gonna say nothing about it like that about me.
Fortunate naming, because it has nothing to do with dark matter. It has nothing to do with being dark.
We didn't hear anything you said, Franco. You was like somewhere else in the
You're on a stroll. You're losing signal.
Hey, Franco, if it's not curving, what's it doing?
Yo, did anybody hear him say this is the distinct reason why these abstract constructs over here is different than this abstract construct over here? Did anybody hear it?
I heard.
Y'all did, like,
differences.
I run that.
But I think he missed the question though. Like, if you were trying to say, like, why are they both? Why are they both plug and play? Right. That's essentially what your question was.
Right. Because that's like the main point. It's like, okay, you trying to say, like, it's not important that there's not observable in reality, because we can calculate it and we can make predictions after we do all these different type of implementations of whatever the hell. And it's like, well, that sounds like what they did over there too. It was like y'all doing this on a quantum scale, y'all doing this on a galactic cosmological scales, like y'all just doing this shit all over the place. Every time it don't work, y'all just implement something, unless y'all can show me what is distinctly different about the two. Otherwise, it just seems like common practice every single time y'all framework fall apart. That's why I wish that get like so upset sometimes. He'd be like, bro, I'm just trying to talk to you man to man, like just on some real shit to see exactly what a physicist is thinking about this. But it's hard to have that conversation if you're not even going to be, meet me halfway, bro. Like I would never think that was Franco back? My bad. I ain't never think I would ever hear a physicist say like that the reality doesn't matter. Like I just never thought like that would ever be a thing to say. Like, never heard about it. Because physics is about trying to explain our reality, right?
Again, the way to hear about this is to learn physics step by step. Again, this is my suggestion, not only mine. I'm serious.
I have a question. I've been trying to understand fields, like the definition of a field, and so what I've gotten so far is an intensity or a direction. I was wondering if you could just elaborate on just the field definition.
A field definition is something different in classical physics and in quantum physics.
Okay, quantum.
Yeah.
Let's go with quantum, because I feel like that's the more accurate science, I think.
Yes, but it's very difficult. It's something which is defined mathematically. Its fields are coordinate-dependent operators acting on so-called Fock space, which is, for instance, a space which is defined by.
Okay.
I don't know
Okay.
how to do that. It's very difficult. You have to start from the vacuum and then define something which is a so-called construction and destruction operators, which are something that acts mathematically on a space, mathematical space. And then when you apply construction operator to the vacuum, you end up with a particle which has a certain momentum, say, for momentum. And then you have that the fields are actually superpositions of these creation and annihilation operators acting on basically on the vacuum, and these operators are point dependent, where point means point in 4-dimensional space, meaning x, y, z, t.
Right.
But
Okay.
it's a field.
Okay.
A
So
field
I
in
got
classical physics is a value. It can be a value, for instance, the pressure, air pressure, or air temperature is a scalar field, because at each point in space and time, you have a value, one single number. So it's a scalar field, meaning it's a function of space and time, one valued function, meaning that you have to each point in space and time, you associate one number. Something like an electric field is something, or a gravitational field is something that to each point in space and time associate a vector, meaning an intensity and a direction. Something that needs 3 numbers in order to be described. Then you have tensor fields, and you have very much more complicated things. But this is in classical physics.
right. Okay.
Quantum field theory is really very difficult to grasp.
I got the gist of it. It's just, what you said was it's basically a coordinate system imposed on space, right? A 4-dimensional
The
space.
coordinate system is the basis, is what you define fields on. Actually, it's actually what you define fields on in quantum field theory is the vacuum.
Right.
Something in the vacuum, and a so-called Fock space, which is a space where a number of particles exist or do not exist with definite, for instance, values of their form momenta. It's something like this. And then you have fields are operators which act on this space.
Space, right. So let me ask you a question. So the operators, what do you guys interpret these operators as? Are they, because I'm interpreting them as vortexes. Is that a correct interpretation? Or incorrect?
No. I wouldn't say that.
Okay.
For instance, the creation operator on the vacuum creates, say, a photon with a certain momentum and energy and direction. So
right, but how is it doing that? So that's what I'm trying to figure out. Like, how is this? So mathematically, it's doing this, but this math is correlating to something that's there, right? So what is it?
Yeah.
What is the math explaining is happening as this for this creative process or destructive process?
It's trying to the theory, the quantum field theory, came up because it was normal quantum theory was not accounting for the possibility of particles to be created and annihilated, which is what was observed with the antiparticles coming into the play. antiparticles can be created in couples. You can have a photon hitting an atom in a bubble chamber and produce an electron-positron pair. This was observed, and so you have that particles which didn't exist before, they exist afterwards. And this also happens in radioactive decays when you have a nucleus, cobalt nucleus, which
So they're interpreting what's they're interpreting what's happening, right?
They emit photons and they emit neutrinos, which were not there before. They were created out of nothing, and so you have to account for that. And the formalism explaining this is the quantum theory, which allows for particles to be created out of nothing with certain rules, of course.
Now, see, all right, so that's exactly the crux of what I was trying to get at, is what you just mentioned in the past couple sentences. So I'm trying to find out where this whole create out of nothing is coming into play, because if these operators are attempting to describe a field that is there, then there's something there that is being, that's being used, right? So when you're smashing particles and you come up with, there's other particles that pop out, and there's two of them when there should only have been one or something like that, but it's still the medium is still there, right? Because these coordinates are imposed on space. But then, so what is the space that you guys are talking about? It can't be nothing, right?
Yeah, you have that. This is, in a way, why people say that the vacuum of quantum theory is not really empty, because it's full of fields, full of, for instance, in the Higgs mechanism, the vacuum is full of the scalar field called the Higgs field. Right. So it's what it is. What is it? Again, it's an operator which has some so-called expectation value on vacuum. Okay, I wouldn't know how to express this in a better way if you not use mathematics. So it's
no, that's fair. I think because you kind of answered the question, so I appreciate you, brother.
The point is as to what Witsit was saying yesterday. Yes, in a way, it's true that it's used this kind of a metaphor and saying that the vacuum is, for instance, theoretical physicists use the term vacuum polarization in order to refer to the, for instance, corrections to the mass of particles, such as the Higgs boson, just the electron itself. They use the term vacuum polarization for some terms in the calculation, which is due to sort of create in quote unquote creation of and destruction of virtual pairs. But the point is, you cannot in any way, if someone like Witsit or whoever wants to call this the new ether, okay, you can call it whatever you want. As I said yesterday, you can call it Josephine. You can call it whatever you want. The point is that you need to tell us how it behaves and what consequences it has on observable facts, such as the electron mass, the electromagnetic moment, and whatever, and simple processes. And the fact that it's not considered to be empty, for instance, because of the Higgs field, which explains the masses of the gate bosons and the masses of the fermions. It's in no way relatable to the ancient notion of ether, because the ancient notion of ether was something that made theories such as electromagnetic theory non-invariant for Galilean transformations and for Galilean transformation. Yeah, you had to make introduce relativity in order to make electromagnetism work. The previous idea was that there was that electromagnetism was not frame invariant, whereas the current theory is totally Lorentz invariant, and all these fields and all this polarization vacuum and everything in quantum theory is by construction Lorentz invariant. It has to be. It's imposed in theory. So even if people talk about new ether, even if Dirac thought about something like this, he did not question one single minute the Lorentz invariance, which was established and is a tenet in modern physics for 1 century and more.
Okay, cool. We got Chrissy with their hand up.
Yeah,
it's just weird, bro, that he be wanting to get the last word when Witsit not around. Like, I peep what you be doing, bro. You be like running. Hold on 1 second, Chrissy. You like to run to the timeline. You saying a whole lot of stuff.
I don't.
Then you be the one. Hold on, I'm talking. Then we're gonna get to Chrissy. You don't get to talk. And then when it comes to situations like this, all of a sudden you run up out the space when nobody is yelling at you, nobody calling out your name, no reason for you to get upset. Then you leave, and then you want to come back and then finish what you want to say without the refutation. I just think that's a little bit weird, bro. Go ahead, Chrissy.
I have a question for Franko. What exactly do you observe when you observe a particle? Do you observe a graph? Does the computer show you a graph that indicates with mathematics that something must be there? Or do you actually see something? Because I want people to understand exactly what you see when you do these experiments, let's just call them that.
It depends which particle, but of course you always see something on some instrument.
Okay, so you see a value on a graph. You assume it's a particle. It can be something else. It can be a measure of a field. It can be anything else under the sun. It's just a number in a computer. That's what you see.
Okay, that's what you see when you go climb a scale and weigh yourself. You see a number on a scale. How do you know that is your? How do you know that what you are actually hearing from your device is my voice? Is actually a real person? You're actually hearing the output of some electronic circuits in your device, and you're interpreting it as something, as some reasoning done by an external brain that you don't know. You don't know if my brain exists. You're only looking at the display and hearing.
Let me finish.
By some electronic devices. And the same is with whenever you measure anything, you don't see the thing. You measure.
Franko, did you interrupt?
You measure things.
I don't think he interrupted. She paused. Like.
Okay, I just came back and I heard her say, like, can I finish? Hey, Franko, speak to us right now, like how you was speaking when your friends was next to us. You know, like with like the upbeat, like chuckles and like the cool laid back tone. Like, don't get turned up now that you not around the people that you want to fool into thinking that this is how you always talk to us. Talk to us like you was talking to us when you was around them. Go ahead.
The reason I speak different with my friends is my friends do not imply that all of our community is a community of either stupid people or liars, which is what you do. I'm sorry.
No, I didn't.
Your implication is that all physicists are either stupid or liars. Because they all
No, I didn't
believe the Earth is a globe. They all believe stars exist. They all believe what we are observing from telescopes is actually telescopes orbiting the Earth and things like that. They all either so stupid that they don't realize it's a scam, or they are liars for centuries. This is why
What I'm trying to
you
get
definitely
at.
told me that acceleration don't have nothing to do with motion, but I digress.
Chrissy, he's not pointing you out.
Yeah, but if he says we all do it, he's putting us in the same boat, and that's not fair. And we don't compare apples to pears, which he did. And actually, scales can point wrong. I have a scale at my parents' house that shows I'm 53 kilos. I have a medical scale at my mom's medical practice that shows I'm 54 kilos. I have one at my job that shows me I'm 53. So even the scales aren't really a good measuring tool. Nothing is really perfect.
that they're not.
What I was going on was the fact that the computer spouts things that are based on equations placed there by programmers and researchers such as yourselves based on assumptions you have made, you as an entire community. You're not lying. I'm not accusing you of lying. I'm just trying to let people know that it's not infallible. Any computer will point out it is reading in a way it was programmed as. Okay, so if you program it to show you that this measurement is a particle, the computer will not lie. The researcher that sees the particle will not lie. He sees the particle, period. But that particle can be something else because nothing has been observed factually.
What
It was just
the definition of observe?
it was just an interpretation of data.
What?
And the interpretation of data happens in the backend of that particular app that you use to do your calculations and spout out the graphics and everything else.
How do you define observation?
Experiments, like provable, like repeatable experiments. Anything else is just assumptions.
It,
Assumptions. We assume that that measurement tells us that this particle must exist, or the lack of that mass over there in that galaxy
is,
must mean there's missing mass over there.
is,
Those are just assumptions. Period.
I'm sorry, it doesn't work like this. It's if you jump on a scale, if you climb on a scale, you're seeing. You said something like the scale I have in my home, in my mother's home, or whatever, does not give you the right answer. How do you know that? How do you know that? How do you trust one against the other? You have
I trust none.
you have
That's the point.
you have a
I make an assumption that I'm about that weight. About that weight.
yeah.
That's not an empirical weight.
How do you know?
I'm about that weight. And weight fluctuates. And every device has a measure of flaw. Every device, whether it's computers or analog.
So
And
how do you,
so two devices may measure the same thing and get different results for one. What I'm trying to say is actually helping your case because
no, you're not.
it makes you guys not liars because you're not. You program your
It,
uh,
it makes
tools
not doing.
according to your knowledge, right? You program the app to see and check in your experiments for the X particle according to the math you know, the science you know. And the computer just validates that. But it can be something else. That's what I'm trying to get at. You just see a graph, you just see math. It can be something else. It can be a dot in a field, and you are just measuring that specific pinpoint location. You don't 100% know. You can be convinced, you can, but you truly can't 100% know because you can't do it yourself.
No, it's not it's not the way physics works and experimental physics works and any measurement works. Again, how you said, I know that that scale is wrong because I know I presume what weight I am.
No. I said I don't believe any weight. I just
Chrissy,
assume
let
because
him
I
finish.
tried
Let
to
him finish. He
see.
let you rock.
Yeah, but he misinterprets what I said,
You,
and
But
that's
let
not
him
fair.
finish. You can correct him after.
you misinterpret what I say and whatever physicist is doing and whatever measurement and how every measurement is done since the beginning of experimental science. It's this: you have you have an assumption, you have an instrument, and then you have ways of calibrating the instrument. So if you say, I'm sure that I'm almost certain that scale is wrong, is because I know by some other presumptions or whatever what my weight is. And so if I see that I weighed 2 kilos, I say the thing is wrong. And the same happens with what you see on graphs when you plot out some measurement with any measurement. You can any measurement means implies that you are reading out an instrument, and that instrument is flawed. And the way you can make sure it's not flawed, you figure out ways of calibrating the instrument. Because, for instance, you calibrate a scale by using something that you know what the weight are, or you define a sample weight. You define that one cubic centimeter of water is 1 gram. You then weight this, and you read something on a scale, and then you put something else, and you find that it's twice that. So you say that's 2 grams. Of course, you have to calibrate the scale and see that if you put 1 cubic centimeter, it reads 1, and then if you put 2 cubic centimeters, it reads 2, and if you put 10 cubic centimeters, it reads 10, and so on. So you have to make sure that the reading is calibrated and is linear and is behaving as you wish, and then you can weight something else and decide how much you trust that. On the fact that you are never certain, this is the first thing they tell you when you learn physics and when you learn experimental physics. You are never certain of anything 100%, because 100% certainty is not something that is even conceivable in physics. You are not certain 100% and then the sun will rise tomorrow. Nobody is. You have a high confidence.
Okay.
Yes, this is what the physics attitude
Okay.
was anything. You never have the 100%. That's why people were freaking out when the LHC was going to start. Before the start of the LHC in 2000, some conspiracy theorists or whatever in Germany came out with a theory that the LHC would have produced black holes that would have destroyed the whole universe, and they were trying to block the construction of the LHC because they were afraid that there was a tiny possibility that the universe would be destroyed by the LHC. And then a friend of mine had to publish a report, a 100 pages report, trying to convince governments that this was not the case. And there were TV shows with a press going to physicists to say, "Are you 100% certain that this will not happen?" And of course, they would no, because we're not certain, 100% certain of anything. We're not even 100% certain that by, as my theoretical physics friend says, when you open a jar of jam, this will not cause a perturbation in the universe that will destroy it. You're not certain that will not happen, and there are probabilities for this.
Franko,
this is physics.
hey.
This is what you learn in physics from.
No, this is a part of physics. I can show you physics that actually demonstrates reality, and I know the frequency on which concrete dissolves into sand. Precisely. Precisely. Physics is precise. I build buildings precisely so that you people don't die.
No.
Do you understand?
It's not.
We build them precisely because we can kill you. So we don't want to kill you. So if physics is theoretical, then all you people are in danger every single moment of the day. And as to restate what I said about the fact that even machines make mistakes, I gave the example of the scales because you compared apples to pears. Scales are not computers, one. But I said I don't believe any measure of any scale. I just assume because three are giving me similar values that I'm somewhere in that value range. I didn't say I'm that particular or that particular or that particular. Okay?
No.
So don't
Isn't it a mix of
misinterpret
both?
what I said, please.
Isn't it a mix of both, guys? Like, isn't it just like, yeah, we're as precise as we can possibly be, but he's like on, as far as being 100% precise, we're always like 0.001 off or whatever. Isn't it
No,
kind of a mix of both?
D369, I'm not talking about this. I'm talking about the idea that using a computer to measure stuff, which is what they use, because on that scale, there's no such thing else. You can program it according to your equations. You can use those equations and tell it that if he finds that specific value, that means it's a particle.
That's
But he
not what
may
I'm talking
find that,
about.
yeah,
I'm talking about
that
what you
was my
just said.
question. That
I
was
know
my
I'm
original.
not talking about your question. I'm talking about what you just said, where you were like, I do things precise. I am
Yeah.
precise. And I'm saying like, yeah, he does things precise too, but he's just saying like, yeah, there's always room that we're never
No.
100% precise.
Well, in statics, there's no room for not 100% precise. We actually put values in bigger than they are just to be sure that nothing goes amiss. It's not the
No,
same
I'm sorry,
kind
Yeah,
it's
of
not
I
true.
think Franco's
No,
saying that
no
even
measurement
though you consider that as
is ever
100% precise, it's
100%
not
precise.
100%
Ever.
precise. Yeah.
Well, that's a relativity
Can you
standpoint, not a practical standpoint. I don't believe in relativity because I don't believe
hear me?
everything is relative.
Yeah,
There
we can
must
hear
be
you.
something that's concrete. There must be. This
Can you hear
rock
me
is a
now?
rock. It's not going to transform itself
Yes.
into a frog, okay? Thank you.
I think Franco had to drop. Maybe he couldn't hear everybody.
No, Franker got activated because they don't like being questioned by some other people who are just as articulate or maybe just as good at
N-
presenting arguments.
Nah. I literally heard him
Yeah,
say,
yeah, he
no,
did it
I literally
yesterday
heard him
too.
say, hey, can anyone hear me twice? So maybe you didn't hear him say that.
Another 24-hour space. It's 333 somewhere for someone.